Okay, I want to do an example involving Coulombs law, and there's two methods one can use. I really want you to focus on this method. So in this video, I'm going to show you basic method for finding the force, for example, on three stationary charges. In this particular example, I'm going to do three stationary charges that are in an equilateral triangle situation. And so the length of the triangle is 1/2 meter long. It's a contrived problem. Okay, it's a long distance. Okay, and all these angles, since it's equilateral, 60 degrees. Since this is our expression for Coulomb's law, and I want to find the force on this top object, or this top charge due to the other two, what I'm going to do first is I'm going to draw a free body diagram. Then after I draw the free body diagram, I'm going to actually find the magnitude of all the forces. And then I'm going to resolve all the forces into their x and y components. This is Physics 205. Your Physics 1 class. And then I'm going to sum the forces in the x direction together. And then I'm going to sum the forces in the y direction together. So I can get the total force in the x direction and the total force in the y direction. Then I will use the Pythagorean theorem to find the magnitude of the total force, and I'll use the inverse tangent function to find the direction. Of course, I can also write everything here in unit vector notation, and you'll see both in my example. So the example I want to do is this. And so the first thing I'm going to do is I'm going to draw a free body diagram. And it's important to realize that I'm really looking at the force on this object. I know there's forces on this object, and I know there's forces on this object. But the object I'm interested in here is this one. So I'm only going to draw the free body diagram on the object I'm interested in. That's how you do these. That's how you do problems in general. So I want to look at charge 2 and charge 3. This charge is negative. This charge is positive. And which means that this object is going to be attracted to this object. So that means that there's got to be a force in this direction. This is a force on 3 due to 2. So I'm going to write it like this. When you look at these two objects, they repel each other. So this top object is going to want to move upward. And I'm going to call this F3, 1. This is the force on 3 due to 1. Then I can resolve the forces into their x and y components. So both of them are going to have a component in the forward direction. One's going to have an upward component, and one of them is going to have a downward component. Let me extend this line. From geometry, this angle is 60 degrees. That angle is 60 degrees. Then I'm going to write the x and y components of each of the forces. So this top one, F3, 1, sine of 60, F3, 2, sine of 60, but this one's negative because it points downward. And now let's look at the horizontal ones, which are going to be hard to draw for me, so I'm going to come over here. That one over there is going to be F3, 1 cosine of 60. And this one is going to be F3, 2 cosine of 60. So just follow the process systematically. Just follow the process I listed there systematically to do these. So the next thing I need to do in my list is to figure out the magnitude of F31 and the magnitude of F32. And I'm just going to use this equation, making sure I put in the absolute value of the charges. So, by the way, I need to remind you, 1 microcoulomb is 10 to the minus 6 coulombs. And 1 microcoulomb squared is 10 to the minus 12 coulombs squared. Let me show you why I do that. I'm trying to save space, so I write things differently in these problems. So I want to calculate F31. So I put in, and I'm not going to put in units here because I'm going to run out of space on my board. I apologize for that ahead of time. So let me put in what K is. Q1 is 2 microcoulombs. I'm only going to put 2 here. Q2, I'm sorry, well not Q2, but Q3 is 7 microcoulombs. And I know that the conversion here is 10 to the minus 12, so I'm going to put 10 to the minus 12 here. That way I don't have to write this number out in scientific notation twice. And then I divide this by the L squared. And if you use your calculator, what you'll get is F31 is equal to 0.504 newtons. Now, when I do F32, I just have to change one number. I just got to change this from a 2 to a 4. Remember, I'm not putting a sign in. The free body diagram is telling me the directions. All this is doing is giving me the magnitude of the force. So I'm going to change this 2 to a 4, which all it does is double that number. And so now I have that. And so once I'm done with that, then I got to find the x and y components of each force. So I got to plug in these numbers here, 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 and here. Okay, so I got to plug in that value. This value here and here. This value goes here and here. Okay? So let me erase this so I have space. So let's start with the top one. F31 cosine of 60. So that's this guy. And this comes out to about 0.252. F31 sine of 60. And let me see what value I have here. Can't remember if I wrote it down. I'll use my calculator real quick. I get 0.436. So let me write this force in IJ notation. Now when I do the other one, And I go F3, 2. This one's going to be negative. This number is twice as big. So this comes out to be 0.504. This is what you get for F3, 2, the bottom one. And so when I put these numbers in, now I have these two forces. All I'm going to do now is add together the components. So the components, when I add these together, I'm going to get 0.756 newtons in the I-hat direction. And when I add these two, I'm going to get negative 0.436 newtons in the J direction. And now I have it written in IJ notation. Okay, so this is a unit vector notation. But if I want to write it in terms of magnitude direction, then I have to use the Pythagorean theorem. I got to take this squared plus this squared. And when I do the work, let me check my results, I get 0.873 newtons. And then to find the angle, theta, I take the inverse tangent of the y component over the x component. So the y component is minus 436. That's the x component. And I don't have to put in the units because the units will cancel out. And so this will give us minus 30 degrees. Minus 30 degrees with respect to the x-axis, or 330 degrees with respect to the x-axis. Now, before I go on, I got to make sure that the calculator is not lying to me when I do this. I notice that the x component, the y component is in the fourth quadrant. The x component, so this whole thing is in the fourth quadrant, right? And the inverse tangent function works in the fourth quadrant, right? Because I know y is negative, x is positive. Remember, if we were in the second or third quadrant, I would have to add 180 degrees to whatever a calculator gives me because the calculator doesn't know how to handle the values that are in the second or third quadrant. So, for example, if these two are both negative, we'd be in the third quadrant. We'd have to add 180 degrees to our actual value that the calculator gives us. So be careful with that. So that's it. That's all you have to do in a problem like this. You have everything you need to know. Now, an interesting question that one can ask is, suppose I had the following. Again, equilateral triangle. We'll make this 7 microcoulombs, but I'll make the bottom two the same. I'll make the bottom two both 2 microcoulombs. So this problem here, which I'll highlight, because I have too much space to make work. This problem here is actually very easy. Because it's an equilateral triangle, all the distances are the same, so all my r's are the same. And the Q1, the Q's are going to be the same for both pairs. So what's going to happen is these arrows are going to be the same length. So when I draw the free body diagram, you're going to have two arrows are the same length, but these are both positive. You're going to have repulsion in both cases. So maybe let me erase this example and draw a better picture. We're going to use symmetry to solve this problem. There's symmetry. The symmetry causes some components to cancel. And that's what you want to say in a problem. You say, there is symmetry in the problem, components will cancel. And that makes my problem easier. So let me redraw this. And let me draw the free body diagram. Again, remember, this is an equilateral triangle. So if I were to draw the force between, the force on this guy due to this guy, it's repulsive, it'd go like this. And this other force would be repulsive like this. So the lengths of those arrows are going to be the same. And the reason why is because in both cases the distance is the same. And the Q1s and Q2s are going to be the same. Which means that the X components will be the same. And the Y components will be the same. So if I were to resolve this into X and Y components, if I were to resolve this into X and Y components, you will see that these two are in opposite direction. Because the angles are the same and the lengths are the same, those X components are going to cancel. So my total force is going to be twice the Y component of one of the forces. So all I have to do is say it's 2 times K times 7 times 2 times 10 to the minus 12 over the distance squared, whatever that was, times the cosine of 60. I'm done. That's the force. The symmetry can be your friend sometimes, so take advantage of it. It can make the problem a lot easier. But on an exam, when you're doing a problem like this, you want to say, there is symmetry, these components cancel, and then you move on from there. Don't just say, by symmetry I get this, but just explain, give a good explanation as to what happens when you have symmetry. What does it mean? And it's very useful if you have a very complicated problem. If you have 4 of them, and for example, that's a square, take advantage of symmetry. Say, because the distances are the same and the charges are the same, you can eliminate some components. That will make life a lot easier for you. Otherwise, if you have 4 of them, you have to go through this 4 times. It's a lot more work, sorry. Okay? All right, so I'll stop here.